Alright, welcome to this episode. This video is provided by the Offshore Craftsman Society. I am number 12 paratrooper. This series shares my personal insights on using SESAM during my research. It helps offshore engineering graduate students understand the software. This involves no unauthorized cracking, internal materials, or official tutorials. It is for non-commercial academic use only. This video has no connection with Ding Wei and is not official training. In this episode, I plan to guide everyone through the calculation of air gap. First, let me explain what an air gap is. The air gap refers to your offshore structure. The lowest wave-affected part of the structure is usually the edge of the deck's bottom plate or the perimeter of the box girder. It is the vertical minimum distance between this point and the instantaneous sea surface. For example, here I have a ship with a helicopter platform. So, for this helicopter platform, let's say, I want to look at the distance from this point on the platform to the sea surface. This height is what we refer to as the air gap. Right now, the waves here are very small. Next, I'll talk about the approach to calculating the air gap. For example, here I have a ship, and the outer surface of the ship is represented by this green line. Now I want to calculate the air gap at this point. The original height at this point is 10 meters. Here is our sea level. Let's assume there are no waves at the moment. The height here is 10 meters, so the air gap is 10 meters. Now, a wave comes in. Let's say the height of this wave is 5 meters. After this 5-meter wave hits, the distance from this line to the top of the wave is 10 minus 5, which is 5 meters, right? But in reality, when the wave comes, the ship will move upward. For example, the ship moves up to here. So what about now? Let's say its height becomes 12 meters. Relative to its original position, it's 12 meters. Okay, so now, what is the air gap? That's 12 minus 5. The air gap is 7 meters. Now let's look at the movement of the ship. Originally, it moved from the 10-meter position to the 12-meter position. So the amplitude of the ship's movement is 2 meters. As for the wave, its original height was at sea level, which we consider as 0 since it has no height. Now, as it moves, the wave's surface rises by 5 meters. So the amplitude of the wave is 5 meters. We use the amplitude of the ship's movement, which is 2 meters. And then subtract it. The amplitude of the wave's movement is 5 meters, so it's 2 minus 5, which equals -3, -3, and then add the original height, which was 10 meters. This is the position under the wave, which is 7 meters. To summarize, the amplitude of the ship's movement minus the amplitude of the wave plus the original height equals the position under the wave. So, this formula is what we use in the context of offshore engineering. The main idea for calculating the position is to use this formula. Next, let's look at what needs to be prepared to calculate the position. First, preparation for the calculation. For example, in the coordinate system, your global coordinate system Z equals 0 is this line. Then your ship. The position of your water line is this green line. In order to make the relationship between the coordinate systems clearer, or to ensure that your imported coordinate system is the same as the hydrostatic calculation coordinate system, we can adjust the ship so that the position of the waterline is set to Z equals 0. For example, your ship model might originally look like this, and in the coordinate system, your ship model is like this. The 0 line is here. Now, it's best to move it here, so that the waterline coincides with Z equals 0 in the coordinate system. Why is that? You can check my previous videos where I explained this. Because the hydrostatic calculation coordinate system is based on the coordinate system you imported, projected onto the water surface. So, if you make the waterline here coincide with Z equals 0 here, then the two coordinate systems will be the same, because it's just projected onto itself. The second thing you need to prepare is to know the position of the point where you measure the draft in the global coordinate system. For example, if you want to measure the draft at the stern of the ship, then you need to know the x, y, and z values of that point in the global coordinate system. Here, I want to elaborate a bit. Because right now, there is very little information online about the details of SESAM, and if some real knowledge is shared, it will definitely harm the interests of certain people. For example, today we're going to talk about draft measurement. So, those who make money by calculating draft for others might not be happy about it. This includes myself. I have also been subjected to some slander and criticism online. Here, I want to clarify that software is just a tool, and what's more, it's foreign software. Look at those good software programs. Do we have any of them domestically? But these tools shouldn't become a barrier to learning. It's like if someone wants to be a sculptor but doesn't even know how to use a hammer, then there's no way they can innovate in sculpture. It's the same as being in this field. If you haven't even stepped through the door, what could you possibly accomplish? So, the people who developed this software have already made it so complicated. I think those of us who know a little about it shouldn't keep it to ourselves anymore. We should just share it with everyone so we can all learn together. Right? If those who understand don't speak up, isn't that just adding another barrier? And in the end, who suffers? It's definitely the students learning the software, right? I myself have also gone through the process of learning software. It's really tough when there's no one to teach you during that process, so I wanted to use the Haigonghui platform to do my part. That's also one of the reasons I joined Haigonghui back then, because here, everyone is, how should I put it, it's quite rare. Everyone shares their resources, and it's truly a sharing community. There are all kinds of software experts and masters here. Alright, that's all for now. Next, let's start the hands-on practice. Now, in Hijiji, let's create a new excavation analysis. First, create a hydrodynamic model. Then, import our T1 file. Here, I'll just use a T1 file because If you want to use T3 or T2 as well, you can, but here I'm just demonstrating. Alright, after we've imported the T1 file, let's create a load condition. The semi-submersible platform model I'm using here is a built-in model. Let's set up the environment for these. To keep it simple, I'll just set a wave direction. I've already introduced these steps in previous tutorials, so I'm going a bit faster here. Alright, normally, the basic setup for our excavation analysis is now complete. Next, if we want to perform motion analysis, we need to create a new one here. WADA, the mode of body points, is right here. Under the load condition, let's click here. Select Specify. Of course, you can also use this grid method, but let's specify one first. Here, I plan to take a measurement at the 0,0 point. This is a motion at the 0,0 point of the global coordinate system. Of course, for my model, there might be nothing at the 0,0 point, but I'm just giving an example. For example, here I measure at 0,0. Note that this water mode of body points, everyone can look into it further. What does this point mean? This point is used to measure the wave height at a certain xy coordinate in the global coordinate system. The z value you input doesn't matter. In other words, whether you enter 0, 0, 0 here or 0, 0, 1 or 0, 0, -1, the wave height you get will be the same. The purpose of setting this point is simply to obtain the wave height corresponding to that xy plane coordinate. Alright, I'll set it to 0, 0, 0. Actually, let me not set it for now. Let's first run a normal translation analysis. After comparing, everyone can take a look at the section and see the comparison results. Note that I haven't set the Vodamo F body points here. Let's take a look first. Let's see what the result is without setting it, and then see what happens after setting it. Okay, the translation analysis is finished. Let's open the post-processing. In the post-processing stage, we click on Print. In the Overwell section, we can take a look at the variables. This means you can check what you currently have. What response variables are there? We can see that the current response variables are force 1 to force 16, which are your first-order wave forces. And your 6 degrees of freedom motions, these are the only response variables. So, there are only first-order wave forces and your motion I/O. Alright, let's close this. Next, let's set one here. For example, set it to 0, 0, 0. Alright, let's click OK. After setting it up, we run it again. Then open post-processing and take a look. See what's different from before. Now, because I set an off-glass point, we have a few more response variables in the response variable list. For example, we have a response variable called elev, which here refers to the elevation of your sea surface. As for your point FKPT1, you don't need to worry about it, that's just the one we set up. Alright, now we want to take a look at this elev. So how do we view it? Go to the display section. Check out this variable. Okay, so this I/O is the one I set up. It's an I/O for the wave height at the 0, 0 point in the entire area coordinate system. How do we? Did I measure this wave height correctly? We can make a very simple assumption. For example, let's set this point very far away. Right now it's very close, isn't it? For example, let's set it to 20,000. Set both x and y to 20,000, which means it's extremely far from your structure. Let's see what happens in this case. Run it. The simulation is finished. Now let's take another look. Print out the variable from just now again. The leave variable. Alright, at this point we'll notice that although the shape still fluctuates up and down, we'll see that the values on the y-axis 0.999 and 1.002, we'll find that these values are very close to 1. Why is that? That's because what it's outputting is the elevation at that x. The elevation at that x, y point in the global coordinate system. Then we perform a review analysis. The result we get is the shutdown result, which is the motion response under a unit wave amplitude, also known as the impulse response operator, IRO. Since this is the motion response under a unit wave amplitude, the waves coming from infinity, the wave amplitude is 1. So, if we set that point far away from the structure, making the structure's disturbance to it very small, what we get is the amplitude of the incident wave. So here, for different wave periods and different wave frequencies, the corresponding wave heights are all close to 1. Is that clear, everyone? Alright, now let's go back to what we were doing just now. Continue to set this to 0, 0, 0. Click OK, alright? Start the calculation. After the calculation is finished, we need to set up the monitoring point. For post-processing, our monitoring point is set in POSWrap. Alright, first we need to click. You can start by creating. To create a very specific point in your project, we take this point as P1. This P1 is the point where you want to measure the monitoring data. Then here, it asks you to enter a coordinate system. This coordinate system is the global coordinate system of your P1 point, and it's the same one you just used when extracting the down both body point. It's right above that point. What does that mean? In other words, aren't you about to set up this monitoring point now? You need 2 points. The first point is the one on your ship's structure. For example, if you want to measure how high the helideck on the ship is above the sea surface, then your P1 is that specific point on the ship. The point you just entered is the one below your ship, close to the sea surface. So, the XY coordinates of this P1 are the same as the XY coordinates you just entered, both are 401. For example, let's say I assume its height is 10 units, okay? Alright, for the next step, we're going to go ahead and build a brand new create a variable. Please go ahead and name this variable mot. Mot means motion. Okay, we select the motion of the first point, which is P1, and then check all these corresponding variables. What does this mean? Because you need to check You need to look at this point on your ship, which is the motion of your P1 point. According to the formula we just mentioned, it's the amplitude of the ship's motion minus the amplitude of the wave's motion, right? So the amplitude of your ship's motion, which is the amplitude of motion at your P1 point, this amplitude of motion is not just the vertical movement. It is coupled from 6 degrees of freedom. This is the motion in the z direction resulting from the coupling of these 6 degrees of freedom. So after selecting all the degrees of freedom, we click here. After creating it, we need to create another one. The expression for this is AG. This AG just stands for air gap. Then change this here. The third one. After changing it to the third one, on the response side, we need to enter MUT, which is the one you just created, the one for P1. The motion of P1 moves in the numerical direction, which means your ship is moving in the numerical direction. We set its factor to 1 and include the performance. What does it mean to set it to 1? You can think of it as a formula. In this formula, the value of MOT is 1. It's not 100 million, it's just positive 1, which means there's an MOT, and then we set another one, MEV. That is your wave height. For the wave height, we set the factor to -1. Alright, now our formula has been written here. This AG is actually a formula. What does this formula mean? You use your MOT to subtract your wave surface height, so here it's 1 and -1. Okay, let's click OK. After linking is completed, we can go to Display. In the Response Wearable section here, find your AG. Alright, as you can see, this AG is the one I just set up. Under 0° wave phase, we can take a look at the value assigned to this AG. Now, the curve we've obtained is exactly what I just mentioned. The amplitude of the ship's motion minus the amplitude of the wave surface motion. The result is the current value you see here. For example, when the wave frequency is 1.5, the corresponding value might be around 1.3 or 1.37. Then, using this 1.37 and adding it to the height I just set for P1, which is 10, right? 1.37 plus 10, so when the wave frequency is 1.5, my value is 11.37 because 1.37 plus 10, right? Think about it, everyone. Think about the formula we just mentioned. The amplitude of the transmitted motion minus the amplitude of the wave motion, which is the value shown in this AG chart here. Then, you add this value to your initial point. The initial height at the very beginning. The initial height I set earlier was 10 when I set P1, so here, 1.37 plus 10 equals 11.37. So, when the wave frequency is 1.5, its crest height is 11.37. That's how you calculate the crest height. This process is very simple. Everyone, just go through what I just did once more. Take some time to review it carefully. If there's anything you don't understand, feel free to leave a comment below and ask me.